Shawn Tornga. I'm coming from Los Alamos National Laboratory, and I'd like to give you guys an overview of the research in my division. The Space Science and Applications group is part of the Intelligence and Space Research Division. So we have a lot of interesting projects, both related to basic science, homeland security, and national security. So just to give you an idea of my background, I've done a lot of gamma ray imaging, Compton imaging, photodiopter imaging, hybrid imaging, as well as algorithm development for real-time imaging and pulse shape discrimination, things like that. So I work mostly on the hard radiation side, or that's my background. I'm going to be talking about some other things in this talk, like space weather or non-ionizing radiation. Those aren't my fields of expertise, but I'll tell you about some of the exciting work that we're doing in our division related to that, as well as a little background information on Los Alamos, the types of skills we're looking for from students and postdocs, and the type of work that we do at the laboratory that you might be able to contribute to. So first I'm going to start off by just giving you an overview of the work that we do at Los Alamos, and then talk about the Intelligence and Space Research Division, ISR, say about how we play into that role of laboratory needs. And then specifically my group, the Space Science and Applications group, I'm going to talk about how we measure and do R&D in the space science field or space weather, and how we apply that to problems that we've identified in our division and at LANL as a whole. This will include space applications and ground applications. So if we start off and just take a mile-high view of Los Alamos, the mission is to enhance global security by ensuring the safety and reliability of the U.S. nuclear deterrent. So we do stockpile stewardship, reducing the global threat of weapons of mass destruction. So we're doing a lot of work with Homeland Security, the Defense Threat Reduction Agency, Department of Energy's NNSA office, and we're solving national problems in defense, energy, environment, infrastructure. Okay, so and we're not just doing defense-related projects. We're solving energy problems, environmental problems, infrastructure, and health security. And here's a look at Los Alamos. We have a large campus, so it's much bigger than, say, LBL here or Livermore. We're almost in square footage size, the size of Washington, D.C. It's a very large laboratory. We have 10,000 employees. We have about 40% of those are technical staff with advanced educations. On average, there's about 300 to 400 postdocs that we employ across the laboratory. And we have many buildings, so we're very spread out across this landscape. So it's about 46 square miles, and we have about 2,500 buildings and over 8 million square feet. So it's a very big lab. And since we're in Los Alamos, this is in the mountains of New Mexico, so a lot of the infrastructure is spread out onto the mesas. So it's a very pretty area, and it's nestled right in northern New Mexico. And we are operated by Los Alamos National Security for the Department of Energy. So the Postdoc Program at LANL. So there's a website at the top that you can go to look at an overview of the Postdoc Program at Los Alamos. You can also just go to the website, and there's easy links to get to it. So the Postdoc Program at LANL, it's one of our main pipelines towards permanent talent at the laboratory. So most staff scientists come in as postdocs before they get converted to permanent staff. Additionally, it's a great way to get experience towards working at other national labs or in industry. So essentially, the postdoc program, it's a 2-year appointment, and there's the option to extend that to a 3rd year. To be eligible, you have to be within 5 years of receiving your PhD. We have very highly competitive pay options for the postdocs, and it offers you an opportunity for conversion to permanent staff. So we have a lot of recent postdocs from some of the institutions in the consortium. We've had 4 from Michigan State recently, and most of them are from the nuclear and particle physics fields. So a lot of what we do, the skills you're learning from nuclear and particle physics backgrounds, like the stuff we're doing here, radiation detection, simulation modeling, transport. So additionally to the postdoc program, we have a graduate student program. It allows you to work towards your master's or PhD at Los Alamos. And there's a couple of options here. You can do this as a LANL employee, so you can be a permanent GRA at Los Alamos. And you can also do it as a visiting student from your institution. So if you're working on your master's or PhD in the NSSC and you'd like to get some experience at a national laboratory, please talk to us. If any of this work interests you, let us know. And we can try and arrange for you to either come out for a couple of months or just come out for a visit and see if we can find a project that'd be interesting to both you and us. And that's really what we want to see from the NSSC is more interaction with universities, generating this pipeline, getting you guys into the labs and gaining experience in the types of things that we do, showing you what skills are useful to us, and seeing how you like it as well. So it's another great source of talent at Los Alamos. A lot of times our graduate students stay on to do postdocs at Los Alamos and eventually become staff. We have excellent facilities and research opportunities. And again, we have a lot of interest working with NSSC students across all of our missions. The program coordinator at Los Alamos is Mike Rabin. So if you have any questions or you'd like to forward your resume to him, you're interested in coming out, give him, shoot him an email or give him a call. You can also copy me on that, and I'd be happy to talk to him about you or with you about any opportunities that we have. So I thought I'd also mention the types of skills that we're looking for. As you all know, before we can do anything, we have to get money to do it. So proposal writing is a very desired skill. So anytime that you guys have a chance to be a part of a proposal, you should really get involved with that and start learning the process of bringing funding in. I'm sure many of you already have been involved with that. But it's something that we do look for when we're looking to hire students and postdocs and staff members. One of the things that's really important as well is software. So it's one thing to build an instrument and test it in the laboratory, but to actually make practical use of it, there's usually some sort of software that's involved. Additionally, a lot of the modeling tools and analysis tools require software skills. So one of the main things we look for, C, C++, Java, Python, JavaScript. And additionally, we do a lot of work in Linux and Unix, so getting experience with those systems is very useful as well. We're looking for people that can do analytic calculations, so just back of the envelope, a quick spot check, understanding the equations and the physics involved with things to make fast calculations. Modeling tools like JAMP4, MCMP, analysis tools like Root, MATLAB, Python, IDL. These are all things we use on a daily basis. It's very important to have experimental and system design experience. So if you have opportunities to work in the lab or you'd like to work in the lab, maybe that's something we can get you to Los Alamos to work in the lab, get experience working on that. Numerical analysis and analysis methods, Fourier transforms, minimization algorithms, principal component analysis. These are all things that we use on a regular basis for almost all of our projects. Post-processing, electronics, computer-aided design. And that we also work with all these institutions. So you may get experience working with us and try out something else, and we can work with these institutions as well as Alamos, Livermore, Sandia, the Remote Sensing Laboratory. We work with the Department of Defense. We work with NIST. A lot of our postdocs end up at some of these other places, either doing a second postdoc or starting their career in one of these fields. We work with industry a lot. Raytheon, SAIC, some of these companies around the Bay Area. In the aerospace industries, Lockheed Martin, Boeing, GE, many, many more. So we really try and work with industry whenever possible as well. So a postdoc at Los Alamos or work at Los Alamos can lead to a career in industry. And it's interesting to know that a lot of these skills can be applied to finance. So we do have people that end up working on Wall Street using the same skills that we use in numerical analysis, data analysis, programming. So Los Alamos is a national security laboratory, and here I just want to highlight three of our main research areas or mission areas. So we have stockpile stewardship, global security, and strategic research. And we're trying to meet the nation's needs in all three of these areas. And so for stockpile stewardship, there's a lot of things you can do with advanced simulation and modeling, hydrodynamic experiments that are performed at Los Alamos. We do a lot of material science at the lab, high energy density physics, and manufacturing capabilities. And specifically in our division, we do a lot of advanced simulation and modeling. For global security, there's nuclear nonproliferation, nuclear materials management, there's defense and space applications, detection R&D, threat response, and international technologies. So in our division, again, since that's what I'm focusing on here, we do a lot with nuclear nonproliferation. We have ties into defense and space applications, and my group specifically is a space science and applications group. And we're also doing, to meet other mission needs, we're doing a lot of detection R&D. So we're looking at new detector materials and building new detection systems, helium-3 replacements, all sorts of technologies. And then strategic research across the laboratory. There's materials and nanoscience, earth and environmental science, chemistry, and energy science. And again, in our group, since we're space science, we're studying a lot of the earth and the environment. So across the lab, our division specifically is touching the three most basic areas of mission needs at the laboratory as a whole. So another thing that we do in our division is we build sensors for either science or programmatic needs. And usually what we do is we use the science from the space science side to drive mission design, build instrumentation, do testing, and then we actually launch the instruments that we build into space. We we do the data operations with them and perform the analysis. We have over 50 years of experience building space instrumentation, so space qualified flight hardware, radiation sensors and detectors. And this includes over 1,400 sensors on 400 instruments on over 60 satellites. So on a typical year, we might launch anywhere from 5 to 15 instruments. There's a lot that goes into those instruments. Here's a couple of examples. The Vela satellites started our main treaty monitoring mission over 50 years ago. So we were tasked with monitoring the atmosphere for near-Earth and space nuclear explosions to verify treaty compliance. So in basic science, we're really interested in astrophysics, space physics, solar physics, planetary science, cosmology. We have active roles in Rover missions to Mars, solar probes, all sorts of satellite missions and NASA projects. We also have our mission-driven applications, so space nuclear detonation detection, remote sensing, radiation detection technologies. And our division covers a large range of the electromagnetic spectrum. So ISR1, my group, we're mostly looking at hard radiation, X-rays, gamma rays, neutrons. ISR2 is our remote sensing group in the same division. They're looking at hyperspectral and radio frequency. And again, so we're looking at X-rays, gamma rays, neutrons, particles, electrons, protons, alphas, in a space environment or as a result of a nuclear explosion. A lot of this is phenomenology based. So we design and develop instrumentation to study one phenomenology at a time, whether it's X-rays, gamma rays. And then all of these instruments, they may respond to backgrounds differently. So we're doing sensor fusion to reduce background levels. All of this requires advanced modeling and simulation, both mission design and system design to meet mission needs. It goes from concept development through prototype development, testing, analysis. We're always looking forward for new technologies, so we're always testing new scintillator materials, electronics, processing, analysis algorithms. We do a lot of data analysis and data mining. So we have instruments on spacecraft that are continuously taking data that it could be very useful for basic science and research. And we do a lot of mining through that data to look for interesting events that we might not have seen before, or any other data that we can get out of the system. So just to go through some of the space applications, the Space Nuclear Detonation Detection Program is one of our main mission areas in the ISR division. So in the late 1950s, the Advanced Research Projects Agency and the Atomic Energy Commission established the VELA program. So basically what they said was they want to be able to detect nuclear explosions anywhere in the world. And so this was a project that was given to Los Alamos and Sandia, and it continues today. So we have a long heritage of designing and building space instrumentation. And this is an important program to the government. So you can see that President Kennedy was actually at Los Alamos. He was a major supporter of this program. And today, we continue to get major support for this program because it's an important problem relevant to national needs. So what is it that we do with this system? Well, we have four main things that we need to do. We need to detect, so did something happen? Was there an explosion? Identify, was it nuclear in nature? If it was, where was it? And how big was it? So we want to know that countries who are signing treaties saying they're not going to do testing really aren't doing any testing. So there's below ground, which we're not concerned with in our group, but there is a program to do hydroacoustic and seismic verification for treaty monitoring. But what we're most interested in is above ground testing. So it could be low altitude, and we have several instruments that are optical or EMP based. If it's in this transition region where it's sort of high altitude but not in outer space, we're looking for optical transmission, gamma rays, neutrons. And space-based, we want to do space detonation. We're looking for gamma rays, neutrons, and X-rays. So a lot of the technology that we're using to do this is similar to what you would use on the ground. So the systems that are being built up at LBL, some of the radiation detectors for Homeland Security, there's a lot of overlap with those systems and the instruments that we build at Los Alamos. So we also try to get involved in the Homeland Security side as well, because it allows us to stay up to date on what the latest technologies are and where the fields are moving, so that we can eventually get those technologies into the mission space for the SNDD program. So basically what we need to do is address the needs of a system to detect a nuclear explosion anywhere above the surface of the Earth, anywhere in the world. We've designed the system across multiple phenomenologies: X-rays, gamma rays, neutrons, optical, EMP. We fabricate these detectors. So we actually build the X-ray, neutron, gamma, EMP instruments at Los Alamos. The optical instruments are built at Sandia National Laboratory. We do integration and testing of those instruments. So we actually put them on the spacecraft. They do integration testing. We have to go through shock and vibe, thermal cycling, everything that goes into launching a satellite into space. And then we have to operate the satellites. So once you get them up there, how do you get useful data off of them? how do you change configuration if you need to, and everything that comes along with operating satellites. So again, it's been over 50 years. It started with the VILA program in the 60s. That transitioned later into the DSP program, or the Defense Support Platform. And we don't actually build the whole satellite. We build instruments that ride on the satellite. And then in more recent years, once the GPS constellation went up, we have sensors, the optical, EMP, and X-ray sensors on GPS satellites. And we also have geosynchronous platforms where we're hosting the next generation of instrument called SABRS, the Space and Atmospheric Burst Reporting System. And we're currently working on the next generation of sensors. So we're always forward-looking. We always have to be keeping up with needs. So the next block of GPS satellites, most of the instruments have already been built and delivered, and they're waiting for launch. What we're looking at now is what's going to go on the satellites in 2020 and beyond. So there's a lot of opportunity to develop new instruments, to add value to a program that has a real big impact on the laboratory in general. So we're called the Space Science and Applications Group, and what is the difference between space science and mission science, and how do those play together? So because we build instruments that go into space, it's very important that we understand the space environment. We have requirements for how much dose a satellite can take, or how long it's supposed to stay in orbit and function. To do that, you need to know what's happening in space with the environment. So we call this space weather and space situational awareness. So there's radiation belts. We design, as part of our basic science mission, instruments that provide us coverage from GPS to GEO of the space environment. So we're continuously monitoring that. We have expertise in doing the basic research in our group and division to actually have an impact on how these things are modeled and how and why things happen in our environment. I'll show some slides later about the radiation belt probes that are actually mapping out the radiation belts and trying to develop a forward-looking model of how the sun and how space weather can affect charging of these belts, and how that, and to do future modeling on that to see how it's going to affect the spacecraft. So the Rdsp Satellite is the radiation belt storm probes. So it's 2 spacecraft that NASA launched in 2012 to study the Earth's radiation belt. So this was a project within ISR. And the primary objective here was to investigate and provide understanding to the point of predicting what's going to happen in the radiation belts, of how relativistic electron and ion populations are changing as a result of solar storms. So these satellites, they have a highly elliptical orbit, and they're going in and out of these shells all the time, measuring concentrations of relativistic electrons and ions. And they're looking at this data as a function of what's going on with the sun. And from that, they can predict what these belts are going to look like. So they can predict dose on satellites and whether or not we might have a problem with some of our instruments. Some more information on the RDSP. So it's really 3 instruments that we have. It's the HOPE, MAG, EIS, and REPT. So this is a collaboration between 3 different organizations. So Los Alamos made the HOPE spectrometer. Aerospace Corporation made the MAG EIS instrument, and University of Colorado makes the REPT instrument. And really the reason we have these is because we have overlapping sensitivity regions in energy to measure the ion and electron fluxes. And you can see here, this is an article from Science. So we also have lots of opportunities to publish some of this basic research. And essentially what we're seeing is that during these storms, we're actually getting the generation of a 3rd belt. So, and that's something that we previously hadn't modeled. We typically use a 2-belt structure to model the radiation belts. But during this particular storm, we noticed the creation and then dissipation of a 3rd radiation belt. And this is really important to us because then we can start predicting what's going to happen in the next storm, and then we can see the data from those storms and compare it to the models and see how well we did. Gamma ray bursts, this is an important field of study for a lot of basic research and scientists looking at creation of the universe and how suns eventually die or collapse. And it's actually the SNDD program at Los Alamos that discovered the first gamma ray burst. It was observed from one of the Vela satellites, and that started an entire field of research. So that was kind of exciting, and we still have a lot of work that goes into that. So our group also has people that are involved with the Fermi Gamma Ray Burst Monitor, GBM. We've been involved in its development and operation since 1997. And here's how, we're doing a lot of instrument design on this. We do simulation and modeling to get detector response functions, like you see here, that ultimately drives instrument design. So again, you're taking simulation and modeling capabilities, data analysis capabilities to really inform instrument design and get involved with projects that have large impact. And you can see the models and the actual as-built instrument. Another space-based mission was the SWIFT mission. This is a gamma ray burst telescope. So something that we found using one of our 3D monitoring instruments opened up a whole new field, and we're still considered experts in our division finding gamma ray bursts and studying them. So the SWIFT mission, again, this is it's the Burst Alert Telescope, which is a large coated aperture. There's an X-ray telescope, and there's some UV cameras as well. And basically, this satellite it's unique in the sense that it can actually identify or locate a gamma ray burst and then slew to a different location to actually get more data from the burst. So gamma ray imaging comes in a lot of these applications. And this is something that came out of our other mission, programmatic mission. Another thing that we're interested in is what's going on in space. Space situational awareness. Where are all the satellites? Every day there's more and more satellites, and the concern becomes what happens when they collide into each other, or how do we prevent that? How do we predict it? And how are their orbits changing? So there's a project in our group called IMPACT. Basically, it's to decide or to develop models about the drag on orbital bodies. So we want to be able to predict not only where something is, but where it's going to be. How is it slowing down? How much uncertainty is there? And it's not as simple as just doing a correction to the orbit, because the drag on satellite bodies changes as a function of space weather or time of day. So it's a really dynamic problem. And we really need to develop models that are better, because as you can see, as a function of time, the number of objects in space that we have to keep track of is going up. And this large jump right here is actually the result of two satellites colliding and creating thousands of pieces of debris. And that could have been avoided had we had better algorithms to determine where things are and what's going to, what might collide into each other. And so it created 15,000 pieces of debris. And those are all of interest to us. Because if we're launching satellites into space and we have a mission to do, we don't want to have to worry about the satellite getting knocked out by another piece of debris or another satellite. So we talked about this, and basically the problem is right here. It's that the best system we had for predicting where things were at the time said that these two satellites wouldn't come any closer than 580 kilometers of each other. And it was ranked number 152 in the system of things to look for. And they ran into each other. So we really need to understand what went wrong there, what changed the orbits, how could we have predicted where they were going to be, so that we can identify these problems long before they happen. So how do we do this? We're basically looking at effects of solar heating, other space weather, changes in density of the atmosphere, and how that affects the drag coefficients. So we're improving the model of the atmosphere. So we're developing models of that and comparing it to measurements that we might get from other data sources or from instruments that we're actually flying. So all of this basically feeds into this impact drag model, and the ultimate goal is to have an end-to-end model with physics-based density, satellite drag, uncertainty quantification to develop a better estimate of collision probabilities. Another mission that you've probably heard of that this division is involved with is the Mars Science Laboratory and the Curiosity rover. So this is a NASA mission, and we built one of the instruments in our group that was on the rover. So the ChemCam is one of the instruments that does remote sensing. So it's a laser-induced breakdown spectroscopy system. So it's actually ablating surface of materials and then doing spectroscopy on the results that come out of the plasma from the ablation. So it can identify materials on the surface of Mars. And that feeds into needs for the IAEA. They've used the same technology to make a backpack version of this to meet other needs of the laboratory. So again, tying in basic science needs, really cool mission to Mars with a rover, and international security needs. This is just some examples of one of the first data sets that came off of the Mars rover. It was called the Coronation, where they took 30 shots on this rock, and across the 3 instruments that are part of ChemCam, they were able to identify the elements that were present there to say that actually this was probably once a riverbed. There was probably water here. Everything that's needed for life as we know it is here. So that was a big result. So far to date, we've done over 35,000 spectra on Mars from the rover at over 1,000 different points. And we're continuing to do this work. We're operating the instruments, and we're finding, that it was possible that life could have been there, that there's water on Mars. We're making big scientific discoveries from one of these instruments that we've designed at Los Alamos that has a major impact. So now I want to talk about some of the ground-based applications. So the first one is the SWORDS program. So this is actually a program that I was able to work on as a graduate student at Los Alamos and finish my PhD while working at the lab, and then eventually become a staff member. And programs like this are actually very useful because the things that you're going to learn developing and working with a system like this are directly applicable to national security needs. So whether it's hardware design or algorithm development or data analysis, these are all valuable skills. So the SWORDS program, it was through the Domestic Nuclear Detection Office. And the idea was to develop a system that could quickly locate and identify sources of interest from long distances. And this was a fairly rapid turnaround project. So it was 18 months from concept to delivery. What we chose to do for our system, working with Raytheon, so we were paired with industrial partners. And one of the other instruments is actually here at LBL. The MISTI truck was another product of this program. So we decided, instead of going with germanium spectroscopic detectors and a coated aperture imager, to go with a hybrid coated aperture imager that uses a random active mask of sodium iodide followed by a position-sensitive array. And we had to do a lot of simulation and modeling because what came out of this call from DNDO was a set of requirements saying, well, it has to go from 40 keV to 2.6 MeV. So you have to do Monte Carlo simulations to say, Well, if I want to capture 2.6 MeV gamma rays efficiently, how thick do my detectors need to be? Energy resolution. What detectors can I use? Which ones can't I use to meet these requirements? The efficiency, 15 photons per second in the photo peak from 100 meters. So how big does my detector have to be efficient enough to meet that requirement? How big does the geometry, or what is the geometry configuration to meet the 2 radian field of view, horizontal or half a radian vertical? There's angular resolution requirements. So if this is going to be an imaging system, how do I have to go through a lot of iterations of simulation modeling and analysis, because you can design a simulation and run it, but that doesn't tell you anything about how it's actually going to come together. You actually have to write some imaging algorithm so that you can prove that you're actually getting the angular resolution that you expect, or do it from first principles in analytic back of the envelope calculations. And all these things have to be done at the proposal stage. And so before there's any money, so the only tool you really have are simulation modeling. So it's really important to know how to do that, how to analyze the data quickly, and show that it meets requirements that are being asked. And there's other things that are harder to do, like demonstrating the false alarm rate, especially if you don't have a final algorithm. And then you also have to fit into size, weight, power requirements. So that comes into understanding the electronics and data acquisition, detectors, just experimentation, instrumentation, design, and how to put something like this together, how big it's going to be, how much power it's going to take. So here's just a quick slide on the actual arrays that we built. So this is the random array with photomultiplier tubes attached, and position-sensitive bars in the back for doing the absorption of Compton-scattered photons or transmission through the mask. We had to develop special PMTs that were less susceptible to magnetic fluctuations, as well as low mass, because we had to keep the weight of the whole thing down because it's in a truck. And this is the final instrument as built inside the truck. So we had 35 scattering detectors, 30 absorbing detectors, and on average we're getting 6.75% resolution, which isn't great, but these are position-sensitive bars, and it's sodium iodide. So it was pretty good resolution. This all comes down to the electronic design, the readout system. It had to have an integrated GPS system because you have to do on-the-fly gamma ray imaging. So you're not only doing one image at a time using a set data set, but new data is coming in all the time. You're adding things together. How do you do that while you're moving down the road? So the algorithm development for this project was very important. Here's some examples of data that we collected during testing. So we needed to see once you do all this, once you've written your analysis algorithms and you've built your truck, does it actually work? So before it delivered to DNDO, we did some testing out in Boston, and what we were doing was variable speed testing. So 5 miles an hour, sure, no problem. We can see the source 25 meters away, just kind of driving right by it. But as you can see, as we go up from 10, 15, 20, 25 miles per hour, the size of the source isn't changing. And this is what we want to see. So you have to have robust algorithms that are capable of doing the same thing in different circumstances. And so this is an example of how we did that. Now as you go faster, you're getting less data. And another thing we were able to do is, since we can localize the source, then you can actually just say, give me the photons from the source area, and you can actually get an estimate of the background that's from not the source, and do a subtraction. So we were able to do very good isotope identification and detection from a single system using coded aperture and Compton imaging fused into one modality that's got a broader energy range of applicability, so low energy to high energy, and it performs over that energy range better than either one of the modalities alone. It's also capable of doing not only high-speed imaging, but very long-distance imaging. So here's an example of a 10 millicurie source. It was placed almost 200 meters from the detector, and within 5 minutes of data collection, it was able to narrow the source down to almost within the pixel of where the source was. Another example of a ground-based project that we worked on at Los Alamos in our division was the Integrated Standoff Inspection System, or ISIS. So this is an active interrogation system. There's a Bremsstrahlung beam that comes out of a mobile container and all the data acquisition and everything that's required and controls. It can send out a gamma ray beam or X-ray beam to something that you want to inspect, and then you can look at what comes back from that system. So we're really interrogating objects of interest from a distance, and then identifying what's there based on what comes back, and if it's something that we need to look at further. So this was sponsored by the DITRA, and it went from 2009 to 2013. Again, we collaborated with Raytheon, MIT, Lawrence Livermore, Oak Ridge, Idaho, and others. And what LANL did specifically was support the design and integration of all system components. So we helped pick out the accelerator, the control system, the data acquisition system. We did simulation and modeling that supported all these decisions. We also worked on the data analysis and the data visualization, and the configuration and control system, the user interface. So there was all kinds of fields involved here. There's software, there's hardware, there's analysis. All of these skills come into play designing almost all of the systems that we work on. Another project for DHS was the Advanced Radiation Monitoring Device. This was, again, a collaboration with industry, with Sanmina. It's an Alabama company, Bubble Technologies Industries, St. Gobain Crystals, and RMD, radiation monitoring devices. Basically, what we designed and built was a handheld radiation detector for neutron and gamma detection. So as an alternative to helium-3, this uses the click scintillator, the cesium, lithium, yttrium chloride, and you get excellent gamma ray detection efficiency because of the high density. You get neutron pulse shape discrimination because of neutron capture on the lithium. And it's all in this handheld package. So LANL developed the readout electronics. So for something this small, you need custom electronics. We found an ASIC that we could use, and we made modifications, developed all the battery, the enclosure, worked with St. Gobain to do the detector housing. And this is controlled by a Palm Pilot or a cell phone. And it has reach-back capabilities to a tablet, so you can link multiple sensors together. And this led the way for us to get really involved with click scintillator. And we're always looking for new scintillator materials to use, and this is how we do it. We work on a project for DITRA or Homeland Security. It helps us identify new materials, and then we're in the process of looking to see how we can use this to meet other mission needs. So this is just showing an example of how you can actually get better energy resolution than sodium iodide in the gamma ray arena from click. And you can tell by the shape of the pulse that's coming out whether it's a neutron or gamma ray. So the ASIC that was developed for the ARMD detector can actually be used to basically set up integration windows on here, and you're integrating two parts of the pulse that are very different or very similar, and looking at the ratio of those, and you can determine whether it's a neutron or gamma. So I just want to summarize what I've gone over. So we have over 50 years of space instrumentation design heritage with the Satellite Nuclear Detonation Detection Program. We have in-house expertise covering all aspects of instrument design, development, integration, and operation. We connect it back to space science. We connect it back to basic research. And we're also looking forward to new applications to meet national security needs. We're always connecting fields of science and technology through multidisciplinary research. So X-rays, gamma rays, neutrons, non-ionizing radiation, optical signatures, hyperspectral, you name it, we've probably got somebody who's looking into it and who's looking to connect with other people at the laboratory. We've done a lot of work with material scientists to develop simulators that we need and try and move forward to develop new technologies that can be used across the laboratory. We're always exploring new opportunities, and it's important to note that while Los Alamos is generally considered a weapons laboratory, global security is our growth area. So I think this field in particular of nuclear nonproliferation, nuclear sciences, threat reduction, homeland security, these are all things that are going to be growing in the future, not shrinking. So it's really important that we get involved with the next generation of students, scientists, engineers, to start getting involved with these projects, because there's going to be a lot of growth in this area. There's going to be a lot of need. So that's all I had for you. Just a special thanks to some of the people that are involved in these projects. Dr. Mark Kippen, he's a program director for the Space Nuclear Detonation Detection Program. Dr. Mark Wallace is the Neutron Gamma X-ray at GEO instrument project lead. Laura Stonehill has done work on the ARMD project along with the CLIC simulator. Dr. Klemenko does the integrated standoff inspection system. David Palmer on the SWIFT satellite. Bruce Barraclaw on the Mars Curiosity rover, and Brian Larson on RDSP. So with that, I think I'm done. Does anybody have any questions for me?
Some of our virtual viewers.
Okay. So I'd like to point out too, if anybody's interested in any of the stuff that I've talked about, please feel free to contact me or Mike Raven at Los Alamos, and we can get you in touch with the right people to start talking about your interests and how that might tie into some of these things. Because we'd really like to work with all of you and have you come out and help us in our needs and help you get some experience towards doing things that might be interesting to you. So don't hesitate to contact one of us, or Erica knows how to get a hold of us too. So we look forward to hearing from some of you.
Thank you so much for joining us, and let's thank Dr. Tornga one more time.